Good morning, Math 30s. We are continuing on with our study of radical and rational functions, and this video is going to be focusing on rational functions. This video will correspond to lesson 3 in your workbook, and just to note that I'm going to do this lesson in 3 parts, so there'll be 3 videos for this lesson. Rational functions were first introduced to you in Math 20-1, and you were told that, okay, a rational is essentially a fraction. What we're going to be doing now is we're going to be continuing with rational functions. And it says here the definition of a rational function, it's a function that could be written in the form of, and then it says f of x is equal to p of x over q of x. And it tells you that both p of x and q of x are polynomials. Okay, so it's going to be fractions with a polynomial in your numerator and a polynomial in your denominator. And then one thing we have to remember with rational functions is whatever that denominator is, so in this case it's q of x, that denominator could never equal 0, right? Because we could never divide something by 0. In a different textbook, it says, you know, a rational function f of x is equal to n of x over d of x. So again, they're just choosing different letters to denote their polynomials. So 2 different polynomials. And then in this example, we would say, okay, for this particular rational function, d of x, so the denominator could never be equal to 0. What this video is going to focus on is this slide here. So what it gives us is it gives us 3 different rational functions, and what we are going to be looking at is we're going to be looking at something that was introduced in 20-1, and that was NPVs, so non-permissible values, was introduced in 20-1. And then what we're going to do in 30-1 is I'm going to further break down non-permissible values, and I'm going to say, okay, when we find non-permissible values of our rational function, they could either be something called a vertical asymptote, or it could be a hole. So vertical asymptotes was introduced in 20-1, but this concept of hole is going to be new. Okay, so I want you to star this bullet. It's going to be incredibly important, as is this second bullet here. So once we actually get to the example of a graph that has a hole in it, that will be this second bullet here. So this question, it says, use the equation of each function to predict whether its graph has a vertical asymptote or a hole, and then we're going to use our calculators to verify. So the first thing I want you to make note of is you have to have your function fully factored. Okay, so when we do this, we're going to fully factor our functions. I want to start with b. So what b says is it gives us this rational function, and the function is 4x plus 2 over x minus 2. So the first thing I'm going to do is I'm going to look at that numerator and I'm going to say, okay, that is not factored. What I could factor out of the 4x and the 2 is I could take out a GCF of 2. So let's factor out a 2, and then I would get 2x plus 1. And in my denominator, I could not factor anything out of that denominator, so that denominator is x minus 2. Okay, so first step is you make sure it's fully factored. The reason why we need to make sure it's fully factored is because for example, when we get to a, you're going to see that factors will cancel. This is an example where no factors cancel. So what we do is we say, okay, this denominator we know could never equal 0. So I'm going to take that denominator and I'm going to say x minus 2 could never be equal to 0. Then I'm going to solve for x, and x could not be equal to 2. In 20-1, we called that a non-permissible value, right? So in 20-1, that was called a non-permissible value. So if I substituted 2 into this equation, it would make this non-permissible because 2 minus 2 would give me 0. And as soon as you have a denominator of 0, we can't have that, right? So what I do is I find what my non-permissible value is. If we have no common factors. So in this example, we have no common factors. What that means is our non-permissible value is a vertical asymptote. So this graph is going to have a vertical asymptote at, and we always have to say the equation of the vertical asymptote, and the equation of our vertical asymptote is x is equal to 2. So you wouldn't say x cannot be equal to 2 here. You tell me the equation of the vertical asymptote, and the equation is at x is equal to 2. Okay, let's look at what that graph looks like. Like, what does a vertical asymptote at x is equal to 2 look like? When we plug this into our calculators, we're always going to plug in the original function. So this was the original function over here. So take out your calculators. It's a good thing just to note that put your polynomials, each polynomial in its own bracket. So put like the numerator's polynomial in a bracket and the denominator in a bracket. So on your calculator, I've got open bracket and I typed in the numerator, close the bracket, divided by the denominator, close the bracket. When you hit graph, here's the graph of a radical function with a vertical asymptote. So what's happening is at x is equal to 2 here, there is an invisible line here, which is called a vertical asymptote. And what happens on this invisible line is my graph approaches x is equal to 2, but it does not touch or cross it. Okay, so this graph is what we call discontinuous. And the reason why it's discontinuous is because of this vertical asymptote here. So a couple things I want to show you. If you go to your table, second function table, and we go to 2, look at what we see. We will see an error. And that's going to tell us in this case that there's a vertical asymptote at 2. The other thing that you could do from your graph is if I go to second function calculate and I calculate a value and I type in x is equal to 2, it is undefined. There's no y value at 2 because there's an invisible line. Oh, it will let me draw this in. There's an invisible vertical asymptote there that my graph approaches, but it will never cross. So this graph is what we call discontinuous, okay? Now what we're gonna do is we're gonna go to A. And B was our example of no common factors, right? When we simplify or factor, there's no common factors, we're gonna have a vertical asymptote. Let's look at what happens for A when we have a common factor. So again, we've got a fully factor. And for A, let's factor this guy. So we have y is equal to x squared minus 5. So you need to be able to factor by inspection, decomposition, and difference of squares. And you need to look at this and you need to realize that that's a difference of squares. Two terms separated by a minus, and both of these terms could be square rooted. That's going to be a difference of squares. So you ask yourself, what's the square root of x squared? And the square root of x squared is x. Then ask yourself, what's the square root of 25? The square root of 25 is 5. And then one gets a positive and one gets a negative. The denominator is x plus 5. Okay, so what happens is, hopefully you could see it, I'm going to actually highlight this, is we have common factors. X plus 5 and x plus 5 is a common factor. Now, before we go ahead and simplify, because after we factor, we are going to simplify, let's state our non-permissible values. Okay, so what was our non-permissible values? So we know that this denominator could never be equal to 0. So my denominator cannot be equal to negative 5, and that's going to be a non-permissible value. So within my function, I could not type in negative 5 or I will get a 0 in the denominator. Now, what happens is I'm going to say, okay, well, what is x is equal to negative 5? It is not going to be a vertical asymptote because that's only the case when there's no common factors. So what happens is if we have a common factor, then x is equal to 5 is going to be something called a hole. There's going to be a literal hole in our graph. Okay, and I'm going to show you what that looks like. So there's going to be a hole at x is equal to 5. So what we have to do now is we always have to say, well, what was the point in the hole? So after we find the hole, they want to know what was the point where that hole exists. And a point is always x comma y. So how we find what the point of our hole is we need to simplify this guy. So when I simplify this and this will cancel, and I'm going to be left with y is equal to x minus 5 is going to be my new equation, simplified equation. This is a function, so f of x is equal to x minus 5. And now I need to substitute out x, and I'm going to put in the hole. My hole is at 5. So f of 5 is equal to 5 minus 5. Sorry, I just realized my mistake. My mistake is this should be negative 5, right? There's a hole at negative 5. So I'm just going to write that here. My x value is going to be negative 5 where my hole exists. So let's change f of negative 5. And to find out where the y value is, you substitute out x and you plug in your negative 5. So negative 5 minus 5. My hole is going to be at negative 10. So on my graph, and I'll show you when we graph this, there's going to be a literal hole in my graph at x is negative 5 and y is negative 10. That is going to be where the hole in the graph is. Okay, so what do I mean by like there's a hole in the graph? Okay, so let's look at the graph and see how we could find this hole. So again, when we punch this radical function into our calculator, we want to do a few things. We always want to punch in the original. Okay, so we want to punch in the original function, and we always want to make sure that the numerator and denominator is in its own bracket. So if I go to my calculator, and I'm going to go to y is equal to, let's clear this, and let's see if I could actually get rid of this. Okay, let's type in the numerator, and the numerator was x squared minus 25. So x squared minus 25. And the denominator, so we're going to divide that by x plus 5. And I'm going to hit graph. So first thing students will often say is they'll say, okay, so Mrs. King, this graph looks like a linear graph. It doesn't look like that radical graph or that rational graph in the previous example. And I would say, you're right, this does look like a linear graph. And the reason why this looks like a linear graph, even though I graphed in two polynomials, is because remember when we canceled? When we canceled, we got to this equation here, which is a linear graph, right? That is a linear graph. However, it's going to be different from grade 10 because there's a hole in this graph. So to find the hole in the graph, we know that the hole exists at negative 5, 10, right? So if I go back to my graph and you look at the graph and you say, okay, I can't see that hole, right? When x is negative 5, actually we have to change our window. Let's change our window. Let's go a bit past negative 10. Let's go to maybe negative 20. So let's change our window to y minimum to be negative 20. And I'm just going to change my scale factor to 2. Okay, I can actually sort of see my hole right there. Here's a couple other places you'll be able to see your hole. If you go to second function calculate a value, let's type in negative 5 where our hole exists. And there's nothing there. It's an empty point, right? There is nothing here at negative 5. The other place that you'll be able to see your hole is when you look at your table of values. And if I go to negative 5, it's going to give me an error. There's a hole there. So we need to know how to graph this hole. And I will show you how to graph it. I'm just going to go back to this page here, and you'll have room to graph your hole over here. So how you're going to graph this is draw yourself a Cartesian plane. And we've got our y-axis and our x-axis. And we know that if I look at my graph, this x value is going to be 5. So there's an x-intercept at 5. And the y value, the y-intercept, let's see, when x is 0, when x is 0, y is -5. So the graph is going to go through -5 and 5. So let's show that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So my graph is going to go through these 2 points here. So I'm going to illustrate that with a straight line connecting those 2 points. I'm going to put an arrowhead at the end of each graph, or sorry, at the end of each line. And now I need to show my hole. So the hole exists at -5 and -10. So at -5 and -10, what you're going to draw is a hole in your graph. And if I had a little eraser, I would erase that little line there. That's the hole in my graph. So it's at -5, -10. That's the point of the hole. And again, what that is, it's an empty set. It doesn't exist in my graph. The third and last example that I want to talk about is going to be example C. And for example C, we have to fully factor it. So there's nothing I could factor out of my denominator. Sorry, my denominator. My numerator I could factor, and my numerator is going to be a decomposition. So factoring my numerator, I'm going to be looking for what gives me a product, what two numbers give me a product or multiply to -10, and what two numbers sum to give me -3. So what multiplies to give me -10 and what sums to give me -3? The answer is going to be 2 and -5. So 2 plus -5 gives you -3. 2 times -5 gives you -10. So remember that for decomposition, what you do is you take your polynomial, so 2x squared minus 3x minus 5, and you break down that middle term and you say, how do I use my answer? How do I decompose this -3x to give me, how do I use my answer to give me -3x? So that would be 2x minus 5x will give you -3x. Bring down this -5, bring down that 2x squared. Decomposition, you'll always get 4 terms. Split your 4 terms in half, and you're going to group factor. You could take out a 2x from this left-hand side, and you will get an x plus 1. And you could take out a -5 from the right-hand side, and you will get x plus 1. If these two factors are the same, you did your decomposition correctly. So my two factors are not x plus 2, it's x plus 1. And then my second factor is 2x minus 5. Okay, so x plus 1 and 2x minus 5. So let's rewrite this rational. And let's fully factor this. So again, the two factors were 2x minus 5. So I'll write that, 2x minus 5. And the second one was x plus 1, all over 2x minus 5. Okay, so again, to review, if there was no common factors, we would have a vertical asymptote down here. But take out your highlighter and highlight that there's a common factor. So this guy and this guy are common factors. What that means is there's going to be a hole. So this example, there's going to be a hole in our graph. So we'll practice that. Okay, so before we cancel and simplify, because that is going to be one of our steps, we are going to simplify. We need to find our non-permissible value that's going to give us the hole. So in order to do that, you take your denominator and you say 2x minus 5 cannot be equal to 0, because that's going to be a non-permissible value. 2x cannot be equal to 5. X could not be equal to 5 over 2. Okay? And 5 over 2 on our graph is going to be 2.5. So we need to ask ourselves, is that going to be a vertical asymptote at 2.5 or is it going to be a hole? Because we have a common factor, this is going to be a hole. So there is going to be a hole in my graph at x is equal to 2.5. That's where the hole is going to be. So now we need to find the point of the hole. Where was that empty set? And a point is always at x comma y. And now I know my x value is 2.5, where my hole is going to be, and I need to figure out what that y value is. So in order to do that, we now get to simplify this equation here. So 2x minus 5 over 2x minus 5 will cancel, and I've got y is equal to x plus 1. So that's when we actually graph this. Even though we're going to graph the original, it's going to look like a linear graph. Let's change that, though, to function notation. So f of x is equal to x plus 1. And now let's take out this x and put in the point of my hole. So f of 2.5 is equal to 2.5 plus 1. F of 2.5 is equal to 3.5. There's going to be a hole at 2.5, comma 3.5. So this value would be 3.5. To quickly graph that to see if we're correct, we're going to graph the original function, and you're going to put numerator and denominators in brackets. So let's go back to our graph. Let's clear this. Open bracket, the numerator was 2x squared minus 3x minus 5. And the denominator is 2x minus 5. So put that in its own bracket. Let's graph this. I'm going to go back to a Zoom 6 standard window because I had changed my window in the last question. So again, it looks like a linear graph, right? Which makes sense because when it simplifies, we get a linear graph. Y-intercept is 1, so everything looks good. You can't see the hole, but you have to know it's there. So where is my hole? My hole is at x is equal to 2.5. So let's see if we are correct. So second function, calculate. I'm going to calculate a value. And when x is 2.5, there's an empty set. So 2.5 would be right about here. There's a little hole there. So we have to be able to graph that. So let's graph that hole. Draw yourself a Cartesian plane. Label your axes, so y and x. The graph is going to go through a y-intercept of 1. The x-intercept is going to be -1. So I'm going to draw a graph that goes through this point and this point. However, at x is 2.5 and y is 3.5, so at 2.5 and 3.5, there is going to be a hole in my graph. And that's how I would show the empty set or the empty point in my graph. One last thing that I want you to write down, and then this will be the end of the first part, is the workbook often calls it a whole because it is a whole. However, your diploma doesn't often use the term whole. What your diploma will call this is a point of discontinuity. So our graph is not continuous, it's discontinuous at that point. So they will often say that a whole is a point of discontinuity. And we could say like a point of discontinuity at, and then x is equal to 2.5. So on your unit exam, I would probably use those two terms interchangeably. I'd use the term where's the whole, or I'd say where's the point of discontinuity. And that's the end of part 1.